Hello, everyone. Let's talk again a little bit about something that we had spoken about earlier, or in another film at least, and earlier, in fact. Regarding the Halliday and Resnick book, 10th edition, chapter 29, magnetic fields due to currents, we talked about a couple special case scenarios, finding the magnetic field at a point due to an infinitely long wire carrying a current I in one direction. We were able to solve that by sort of cutting the wire like at a point at a point that had a line segment that was perpendicular to the point P at which we wanted to find the magnetic field that was present. In other words, there was a line going all the way this way toward infinity and all the way down that way toward infinity, and there's a point P, and we want to find the total magnetic field at point P, and we drew a line that was perpendicular. We drew a line segment rather. We drew a line segment that was perpendicular to the infinitely long line, and from there we sort of, in our minds at least, cut the wire right at the point where the line segment intersected the wire at a 90-degree angle. So the perpendicular intersection of this line segment with this line, for our purposes, the way we had set it up, somewhere, wherever that would have been, the perpendicular intersection of this line segment of length capital R with this infinitely long wire, and then we just took the semi-infinitely long wire here, found the magnetic field that it would create, the infinitely long wire of carrying current I, we found the magnetic field that it would create at point P, and we simply doubled it and found the magnetic field that would be produced by an infinitely long line. Okay, we did that last time. It worked out okay. I did not particularly like my explanation of why we were getting a negative answer when we were doing the integral. We were trying to find a magnitude, and I said, and rightfully I said to you, that the negative doesn't matter. Get the absolute value of that negative answer and you'll have the magnitude. If you don't get a positive answer and instead get a negative answer, the absolute value of either one of those answers is the magnitude. So that's correct. Now, we were getting a negative answer. We could have gotten a positive answer had we done it differently, and I did propose at one point the way that could have been done. Again, I was somewhat less than pleased by my long thought process on tape to try to tell you how that would be happening, and I couldn't really give you the best definitive answer regarding what was going on. I did suggest that you change and regard the derivative under consideration as not being negatively signed, but being positively signed. That I remember saying in one way or another, and that would have made it work at least. But why would it work? Okay, so let's go back. We don't have to do, first of all, we got the right answer. What we did last time, though it took quite a while, we did get the right answer. So there's nothing wrong with what we did last time. We got the right answer. We ended up getting negative answers in some of the attempts that we were doing, but the absolute value of those negative answers would have been and are the right answers. And we had said that that was the case. So we're fine. We got the right answers. Let's see how we can get a positive answer regarding magnitude, regarding some of the things we were talking about. We're talking about the line segment that was here. I wrote a lot of things down here, guys, and we'll think, I may end up erasing some of them, just hook around and talk about it a little bit more. First of all, I guess before we go any further, we can talk about the law of Biot and Savart, and that is dB vector equals mu 0 over 4 pi times I ds vector cross r hat, the unit vector in the direction of r vector. That's r hat. It's a unit vector. It's as big as, its magnitude is as big as 1, and it's in the direction of the r vector. So it's the unit vector r hat. All of this, the entire quantity over r squared. This is definitely an inverse square law. There are numerous instances in physics where you're employing the reality of some sort of inverse square law. Electricity and magnetism, in electrical charges and the attraction or repulsion that each one has for the other is an inverse square law. Gravitation is an inverse square law. When you talk about intensity of light or intensity of sound, how it loses intensity with distance, that behaves according to an inverse square law. This is also the the law of Biot and Savart also is an inverse square law. You saw last time, initially when I was trying to discuss this, there was a typographical error there. That has been corrected. It's corrected as of the last video as well when we were talking about it. We caught it in the first half hour or so of about the 2-hour video or so. And we also, in the notes, have this corrected. And it's here again for you. Essentially what we're looking at, as we said, the differential magnetic field, dB vector, equals mu 0 over 4 pi times I ds vector cross r hat over r squared. That's the law of Biot and Savart. And that's what we're going to do to find out what the magnetic field is, the magnitude of the magnetic field is at the point P, while this right here is the infinitely long line. We said we're going to cut that infinitely long line and find out what the magnetic field is associated with the semi-infinitely long line, and then we're simply going to double that answer and have the magnetic field associated with the infinitely long line. It doesn't matter. The current, is going in just one direction. Now, there's a lot going on here. The way this thing is set up, in all instances, in fact, let us kind of see what we can say here. In all instances, ds vector cross with r hat, when we do the right-hand rule, our thumb goes right into the board. The aggregate sum of all those will be a vector. The integration that will take place will be a vector going right into the board. ds vector cross r hat goes right into the board. ds vector cross r hat. ds vector cross r hat goes right into the board, and that'll happen everywhere, even down the other direction. The way it's set up, there'll be an r vector this way, there'll be a ds vector that way. ds vector cross r hat, bam, into the board, even down here. So the aggregate is going to be right here. Now, if this is a positive, this is the positive y direction. It's in the positive j hat direction. And this right here is the positive x direction, the positive I hat direction, positive I hat direction, positive j hat direction. When you do the cross product, it'll be in the negative k hat direction. If this is positive x values and these are positive y values, it'll be negative z values when you actually do this. Well, many things were happening, perhaps fortuitous more than anything else. We'd have to analyze it a little bit more. We were getting negative answers. We got the absolute value of that. I told you, if you got the absolute value of it, that's all we're looking for, the absolute value of the answer, and that's going to be the magnitude. Can we flat out get the magnitude, even though this is clearly pointing this way into the board? Well, there's a lot to be said, and like I said, let's say a few things if you don't mind. There's some notes from notes that are written here, but before we maybe talk a little more about that, let's say a few things that maybe make a little bit of sense for us, and we can say what we're doing here. Let's do a few notes here, and then time out, and then work our way into some of what's going on over here. All right, guys, I said a few things here. I'm going to say them again, so not to worry. This small r right here in our configuration has great value for us. I mean, if this is a length for whatever snapshot we're taking here, the capital R remains a constant, whereas S varies. It varies from an S value, if you're talking about the semi-infinite length of wire, just this part right here, from S equals 0 going upward toward infinite values in size. Okay, sure. We know that this is a 90-degree angle, as we've talked about. This is S, this is S, this is capital R. Small r is the length of the hypotenuse, which is one of the legs squared plus the other leg squared, the whole thing taken to the 1/2. And that's where they're getting that answer. Now, I wrote some stuff over here that's going to be hopefully of interest for us when we do some of this stuff. We know with this theta right here, there's another angle, 180 degrees minus theta, if we're talking about degrees, or pi radians minus theta, if we're talking about radians. These are complementary angles. The sine of complementary angles are equal to one another. Complementary angles have equal values of sine. So if you were talking about the sine of that theta right here, that's an obtuse angle. Its counterpart, which is an acute angle, its supplement, which is an acute angle, you call it phi, which is equal to 180 minus theta, call a lot of things. This sine of theta is the same as the sine of 180 degrees minus theta. True. If we're dealing with radians, as we've just said, we can do, then it's pi minus theta. Now, radians are the language. They are the language that you will use when you're trying to do calculus regarding, when you're trying to talk about some sort of variance going on between, or some sort of relationship going on between something that has a linear length associated with it, such as ds, because later on I'm going to find a way to express ds as we did last time. It's not going to be surprising to us. What's going to be surprising to us is just we're going to say about the sine of it, what we choose to call the sine of it, given the circumstances in which we find ourselves right here. The answer we give is actually universally right. But I mean, there's applications you can do as long as you're talking about the rate at which things are being done. This is easier done than said, guys. So let's kind of move in that direction. So we got something like this right here. Is it true, as we said all this, there's a number of things that are good to ask. I mean, ds vector cross r hat vector, ds vector cross r hat vector is equal to the size of ds vector, which is ds, times the size of r hat vector, which is 1. The size of a unit vector is 1. So the size of ds vector is ds. The size of ds vector is ds. The size of r hat, the unit vector associated with r, that's 1. So ds vector has size, has magnitude ds. R hat has magnitude 1. Ds vector cross r hat is ds times 1 times the sine of theta associated with them times n normal. In a right-handed configuration, in a right-handed orientation, you'll have, according to the right-hand rule, this cross product gives you another vector that's perpendicular to both of these vectors in a right-handed orientation, and it has the size, magnitude of ds times magnitude of r hat times the sine of theta. Well, if I was talking about the magnitude of this, it simply comes down to this. And that becomes ds sine theta, or sine theta ds, when we're actually doing that. So that's interesting. Okay, we've said that. We've seen this. We were doing it last time. So we can say here, having said this right here, is there a way you can write sine theta? Is the sine of theta this angle on the outside, it's the same as the sine of 180 minus theta. It's the sine of this angle. They're the same thing. If we're talking about supplementary angles, ladies and gentlemen, when we look at how these things are oriented, how we get answers. How do we get these? You know, how they're oriented, what's going on here, and there's the r hat. Well, if this is theta, the sine of theta is the sine of this angle right here, which is the sine of theta equals the sine of 180 minus theta. If this is 120 degrees, if this is 120 degrees, its supplement is 120 taken away from 180, which is 60 degrees. 120 degrees, if this is 120 degrees, this is 180 minus 120 degrees. 60 and 120. Okay, the sine of 60 is the same as the sine of 120, is what we're talking about here. So we talked about that right here. What is the sine here, guys? Isn't the sine of this angle, which is the same as the sine of this angle, isn't that opposite over hypotenuse? It's the opposite over the hypotenuse, and that's, so you can write it like this. Try to give just a little bit more room here, guys, when we do this. Some notes we had on there earlier. So the sine of theta is the opposite, capital R, which is a constant. This distance does not change throughout the problem, but R does change. As you move upward, capital R does not change, but small r does change. As you move upward this way, small r becomes a bigger and bigger answer. Whereas capital R, the length here, capital R, does not change. S keeps changing. It can get smaller down this way. S can keep changing, get smaller down this way. If S gets smaller, small r will get smaller. If S gets really, really big, then small r will get really, really big. But capital R does not change in size. It is the opposite over the hypotenuse. And we got this. Now, we do know the hypotenuse is the square root of the sum of the square of the legs. It is the square root of the sum of the squares of the legs. Indeed it is. Indeed it is. It is, as we said, the square root of the sum of the squares of the legs. And that's indeed true. We got that. Now, that's an interesting point to describe in this whole process. And like I said a couple things here that maybe need, like I said, I think we're going to just backtrack just a little bit. Everything you see here, you're going to see it again, and now it's going to make a little more sense while we're doing it. Let's see what we can say here. So if that's the case this way, and it is, and ds, sine theta is that, and we got, ds is going to be this, so there's a lot we can say here. I mean, ds vector cross r hat is ds sine theta. Sine of theta is capital R over small r. So let's see what we can do here, guys. I'm never really confident as how easily visible some of this stuff is. So I tend to write large to begin with, but I write even larger, I think, sometimes. Sometimes you run out of a little bit of room, though. That's the problem. you get to here, and that's the same as sine theta is capital R over small r ds. So this thing right here, which we certainly see right there, we certainly see that right there, at least for this particular instance, giving us this is the same as that. Well, let's see what we can say regarding that. So you look at, and there's a number of ways this can be done. Let's just do what we can do, and we'll take it from there. Let's talk a little bit. Some of this I don't have to erase. Arguably, maybe almost none of this has to go right now. We can just walk through it, but I'd rather kind of walk through it from scratch. I think you'll get a better intuitive feel for it if we just walk through it live, more or less. So it's up here earlier. I just kind of opted not to go with a particular way that I was initially looking at going at. I just thought it'd be more efficient if I kind of just started that. I started this process in another thought process, in another attempt to do a video. I just didn't agree with maybe the way this could be seen. Maybe it'd be hard to patch this together. So I'd like to start it from scratch if it's okay with everyone. So we're here. There it is. Well, what's going on here? Well, we already kind of just said what's going on here. We said, we said the whole song and dance here, starting at least part of the song and dance, ds vector cross r hat was ds sine theta is the same as capital R over small r ds. Well, ds vector cross r hat is ds sine theta. We said that right here. And ds sine theta is capital R over small r. So this ds sine theta, at least as far as magnitude is concerned right now, we're just trying to deal with magnitude, and I just wanted to kind of display sort of a subtlety in the integration process, or how we can think things out, thinking on our feet, so to speak. So this, as we said, the ds sine theta is the same as ds vector, in terms of magnitude at least. Just in terms of magnitude. This is a vector quantity. The cross product's a vector quantity, but let's talk about the magnitude of this vector quantity. ds vector cross r hat, ds vector cross r hat is magnitude ds sine theta. We said that here. We were talking about it way over there to actually get the answer that we wanted to get. So ds vector cross r hat is ds sine theta. Sine theta is capital R, which is a constant, over small r, which can vary. And that's pretty important. Capital R over small r ds, which capital R is a constant, small r varies. So the sine of theta is capital R over small r, then ds is the ds. So when we do this, you got capital R over small r ds. True. Wait a minute. This thing right here, this r over small r, the over small r can be right underneath here. So, I mean, capital R over small r is the same as, there's a number of ways to go here, guys. I'm not entirely confident of how comfortable people are going to be with some of it. So let's just try to be as comfortable about it and try to make as much sense. This small r comes down here, multiplies with the small r squared, and you got small r cubed ds. True. True. Well, that's your dB. Kind of something you can do here. Tell you what do you say you multiply by r squared on the top and you multiply by r squared on the bottom? Okay, fine. Let me take the r squared on the bottom and put it right over here. The I is I. The r squared that was right here went over to here. That's what I got here. The r squared, so on the bottom, the r squared that was here went over to here, so we got this. The r squared here went, the capital R squared times capital R is capital R. Capital R squared times capital R is capital R cubed over. Let me write it like that if you allow me to, just for visualization purposes. So what's going on here? Well, I want you to look at that very carefully. Let's look at it very, very carefully. What we can say is, that right there, let me go to the left, utilizing all this. You guys okay with magnitude of dB, or at least some semblance of the magnitude? If it's not the magnitude, we'll get the absolute value of it, and it'll be the magnitude. I mean, the answer that we get will have a magnitude of dB, that's for sure. You've got, we've got this. Let me just get a little more room, guys. I'll start. First instinct was to come here to the far level here, and we'll take it. We've got got that. You've got I. What is capital R cubed divided by small r cubed? Isn't it the same as the quantity capital R over R cubed times ds? Yeah, sure is. Sure is. Yeah, I got news for you. It's not really news either, guys. We know it. We know it. Sine theta equals capital R over R. Capital R over R is sine theta. If you cube it, it's sine cubed theta. Okay. So you're looking at this as is. You got it. True. Now what? Well, I'll tell you what. I mean, be nice to find what ds is, and that's kind of something we were, having some issues with. Well, not necessarily issues. I don't want to say issues, but what is ds? ds is the differential change that would take place. In other words, you're talking about. I mean, let me just take a snapshot. Let's move this hypotenuse to anywhere we want. Let's say this is the differential change ds. This was a hypotenuse right here. This is another hypotenuse right there. This angle theta 2, not much bigger, but it is bigger than theta 1. So, I mean, I'm dealing with the outside of the angles. This is the crazy thing, and I tried to talk about it the last time that we spoke about chapter 29. I don't know, perhaps with some level of effectiveness. I don't know, hopefully at least some level of effectiveness. So let's see. Hopefully some of it made sense. Yeah, theta 2 may be bigger than theta 1 as you proceed upward if you're going to be doing some kind of integral. Theta 2 is bigger than theta 1. Yeah, but this guy, we'll call him theta 2 prime, compared to this guy, theta 1 prime. This is the inside guy, the supplement right here is theta 2 prime. The supplement right here is theta 1 prime. This is bigger than that, the inside. The theta 1 prime, I don't know how many things I should write in here, guys. It's a little, if you were going to talk about it, if you talk about the inside guy, this is theta 1 prime, and this guy right here is theta 2 prime. Theta 2 and theta 2 prime are supplementary angles. Theta 1 and theta 1 prime are supplementary angles. Theta 1 and theta 1 prime are supplementary angles. Theta 2 and theta 2 prime are supplementary angles. The inside, as you move outward, the primes get smaller. The primes get smaller. Theta 2 prime is smaller than theta 1 prime. But the corresponding theta 2 on the outside is always bigger. This is always the case. Theta 2 prime is always going to be smaller than theta 2 prime is always going to be smaller than theta 1 prime. If you were going to go this way, go down this way, until it gets to a 90-degree angle. Theta 2 prime, however, is always going to be bigger than theta 1. And that's why the integral gets kind of nuts. Which one are you going to use? We already said it doesn't matter whether you're dealing with supplements. Either one of the supplements has the same sign associated with it. Yeah, but apparently the way they're constructing certain derivatives with trigonometric functions, their primary focus, their initial focus at least, when they're trying to make the definitions of it, are we actually found the derivative of the cotangent of theta, we found it to be -1 over sine squared theta. That's true if you're talking about the theta primes. If you're talking about the inside, if you're talking about the inside angles, as you proceed outward, the primes get smaller. If they get smaller, the difference between a small and a big, the difference between the further away you go, you're getting a theta 2 prime, which is a smaller answer than the theta 1 prime. Theta 2 prime minus theta 1 prime, theta 2 prime minus theta 1 prime is a negative answer. It's a negative answer, so it's a negative answer on the bottom, but the cotangent, but the difference in the cotangents is something interesting. You're getting a bigger cotangent the further away you go to smaller theta prime angles. So the difference in cotangents is a positive answer, but the difference between the thetas is a negative answer. Positive divided by negative gives you a negative answer. That's why you're getting the derivative of the quantity 1 over tangent of theta, which is the derivative of the cotangent of theta. You're getting a negative answer. You're getting -1 over sine squared theta, because the measuring stick is really the primes. But we were looking to do the integration vis-a-vis the stuff on the outside. Well, the stuff on the outside, as you move upward, theta 2, here theta 2 prime and theta 1 prime, theta 2 prime minus theta 1 prime, small angle minus big angle is a negative answer. Theta 2 prime minus theta 1 prime, theta 2 prime minus theta 1 prime is a negative answer. True. But theta 2 minus theta 1 is a positive answer. And the cotangent, the 1 over tan theta function up here is something that is, the cotangent function up here, the 1 over tan theta function here, is bigger than the one down here. So it's big minus small, positive answer, and you got big minus small, another positive answer. Positive divided by positive is a positive answer. The derivative in those circumstances the d 1 over tan theta d theta, being that it is negative 1 over sine squared theta, true in the circumstances they usually define it as, but in this circumstance, the answer is a positive answer, not negative 1 over sine squared theta, but rather 1 over sine squared theta. How do you know it's just an opposite sign? Because the difference, the distance here, one's a negative, or when you're actually doing this, it's an interesting point in its own right, I guess you could say. You could write it a whole bunch of ways. You could say that the difference between these two, we're saying the theta 2, theta 2 prime is less than that. Why is that? Well, theta 2 prime is pi minus theta 2. True. We're saying it's smaller. And you're going to subtract pi minus theta 1 right here. The pi's cancel, and you end up getting theta 1 minus theta 2. Theta 1, so if we were looking at it, let's see here. Let's see, yeah, right, we got theta 1 minus theta 2. This is big minus small. Let me just see here. Let me just write that again, guys. I think it's right, but I'm not incredibly thrilled by it. The prime is the inside. Theta 1 prime minus theta 2 prime is going to be a positive answer, but I want to go to theta 2 prime compared to theta 1 prime, and that's a negative answer. So theta 2 prime minus theta 1 prime, theta 2 prime is 180 minus theta 2. And the other one is 180 minus theta 1. Pi minus pi is 0. Negative theta 2 minus a minus right here is plus. It's theta 1 minus theta 2. Well, theta 1 is a smaller angle than theta 2 is. Guaranteed could be less than 0, just like theta 2. Right, theta 2 prime. Yeah, just like theta 2 prime minus theta 1 prime is less than 0. They're equal to each other. Equals this. True. And the answer, they're less than 0. So there's something going on here. If I was finding, let's get this derivative. Now again, I'm kind of leaving this thing out there. It's all right. Let's leave it out there a little bit. Let's leave it out there. It's okay. There's no contradiction in our logic. So to make sure there's no contradiction in our logic, let's keep talking. Let's elaborate a little more. But let's leave this right here untouched a little bit. We said this. Okay, what does that mean? Well, we already just said that. I mean, this is a very important point in its own right. I mean, theta 2 prime minus theta 1 equals theta 1 prime minus theta 2. Can play this game all day, you guys. This is a big thing. So, I mean, we said minus theta 2 prime equals theta 2 minus theta 1. I can play this all day long, guys. We can go like this, too. We can go multiply this by a negative 1, multiply this by a negative 1, and we got this. Multiply this by a negative 1, multiply that by a negative 1. Yeah, same argument. Okay, so yeah. You're going to get, you can't do a subtraction. If you do a subtraction, what else does this mean? It means, I'll tell you what it means. This is the prime right here. Theta 2 prime. Theta 2 prime. This is theta 1 prime. What does that mean? That means this. If you flip this, if you multiply by a negative 1, you got this, but then you got to multiply by a negative 1 again. Look, I'm just make a long story short. If you're going to go in the same order, associated with subscript 2 minus associated with subscript 1, does it equal something? Its counterpart, its supplement. When you talk about the supplementary angles, if you go what's associated with subscript 1 minus what's associated with, if you take what's associated with subscript 2 and minus what's associated with subscript 1, that's equal to negative 1 times the negative 1 times what's associated with the supplementary angles. So these are two supplementary sets. One supplementary set, subscript 2, subscript 1, do a subtraction. Subscript 2 minus subscript 1, do a subtraction. Great. You got to multiply one of them. Either multiply this quantity by negative 1 to get this without the negative 1 here, or multiply this by negative 1 to get that one. That's pretty important. Basically, delta theta prime equals negative 1 delta theta. And the smaller you make these, if you make it infinitesimal to an infinitesimal level, differential level, then we got d theta prime equals negative 1 d theta. No matter how you slice it, everybody's the same size, but there's an opposite sign associated when comparing one to the other. The primes have one sign, the non-primes are the exact same size, but an opposite sign. And that's where, it's a subtle point that way. And usually the way they're talking about this is they're talking about how it behaves within the structure of angles that are embedded in right triangles. This right here, I don't want to take it away here because it's right here, but on the outside of it, this right here is a right triangle. This right here is another right triangle, and usually you're dealing with, I don't know about usually, I don't want to make blanket statements here, guys. It's very believable that you'd be dealing with the acute angles, or angles that are mostly acute. You're dealing with angles that are embedded within particular right triangles when you're doing the calculus of getting the derivative of a particular function. And that's where, the integral of some of these things can get messy. And that's where we ran into problems the last time. As I said last time, despite the speech, despite the confusion, we were getting answers that were negative, but they were the same magnitude that we wanted. How do we solve it? We knew we were doing all the mathematics correctly, or very confident that we were doing all the mathematics correctly. Just take the positive counterpart of the negative answer that we were getting. Get the absolute value of that negative answer. And that was what we said last time when we ended up getting the answer. So that wasn't a problem. But I'd like to explain kind of the subtlety of what goes on here. We don't just think about, we don't say, oh yeah, this is what it is. This is the derivative of the tangent function. Therefore, I'll use that. we got to actually find out where we're going and what direction things are going and how the values compare to one another. This derivative, this d 1 over tan, this d of the function 1 over tan theta d theta is equal to negative 1 over sine squared theta. I agree 100%. D of the function 1 over tan theta d theta equals negative 1 over sine squared theta. I agree 100%. I agree 100%. If we're dealing with the insides, the primes. If we're dealing with the primes, theta 2 prime, theta 2 prime, theta 1 prime. If we're dealing with the primes. If we're dealing with the outsides, it's a different song and dance. How different? It's merely different by a sign. It's merely different by a sign. How do I know it's merely different by a sign? Because I just told you they don't vary that much. This one's prime, and this one's not. This one's for the d theta prime equals negative 1 d theta. D theta prime equals negative 1 d theta. Delta theta prime equals negative 1 delta theta. Not much of a difference. What's going on here? Well, we were going to use the thetas on the outside. I was going to start at this cutoff right here where small r fell right onto this at a 90-degree angle, pi over 2. Radians are the lingua franca for calculus. Radians most naturally correspond to the length of items that are taking a circular path, that are curving in some regard. Radians correspond most naturally to that, at least in terms of the language. Does it really matter what angle? Man, you can make up angles for all you care. As long as you know how to work with them, you can make it work. It's not going to be as aesthetically pleasing when you do it, but the radian is that aesthetically pleasing. It does. I can convert any kind of angles to any other kind of angles as long as we're consistent. That's not an issue. But when you're doing this, the radian corresponds naturally to what goes on with arc lengths in a circle. And that is very important. It corresponds to the radial length and the arc lengths in a circle in such a manner that's very, very natural, it just works very well, and it's very easy to visualize. So you're using radians on this. And this corresponds all the way across, guys. So you're looking at it, you got what you got. We're remembering this, it's not going to bother us. We said it was going to be the same. And this is one reason some of the stuff I'm talking about is going to work just fine. I think I'm just trying to bring us to the story we're trying to tell here, guys. All right, we said a lot of stuff. I guess a great question would be, yeah, this is great, but how am I going to do an integral here when I got, well, first of all, it's a lot easier to do this integral than you think it's going to be. I, for our purposes, is a constant. Mu 0 is a constant. 4 is a constant. Pi is a constant. Capital R squared is a constant. Sine cubed theta is not a constant. It changes. As this changes this way, the trigonometric values are going to change. Sine cubed theta is the only thing varying here. I is a constant, mu 0 is a constant, 4, pi, and capital R cubed are all constants. Yeah, I know, but theta and ds doesn't work. I gotta write ds in terms of a d theta, and maybe I'm in business. Okay? So, with this in mind, let me try to say a few things here, guys. Now, they're all complementary angles. See what else I could say here as we are talking. So what did we say here? I mean, we said that the sine of theta equals the sine of the quantity pi minus theta. Yes. Also, the sine of theta, the sine of theta equals the sine of the quantity pi minus theta. True. Also true is that the cosine of theta equals the cosine of the quantity 180 minus theta. Yeah, in certain places. You got to kind of, when you're dealing between 0 and 180 degrees, let me talk about that. And in fact, that's true. So there's a lot here, guys. We kind of got it, so we're not worried about it. That's pretty fascinating stuff, actually, if you think about it. What we have here, and we'll see what we're going to do. And we remember some things, and again, I always forget, guys, that you guys have the feature of being able to go back and figure out what's going on, or at least see what went on earlier. What's going on here? We already said it, and let's just kind of just say it again. Let me just stay with the pi's, I guess. Sine of theta equals the sine of 180 degrees minus theta. Or if you allow me to use radians, well, let's just not write them over and over, guys. You know when I'm talking about pi, it's in radians. And if it's in degrees, it'd be 180 degrees to get this. The cosine of theta, and I don't want to get too fancy with this. I'm not going to look too much along the unit circle. We could do that. It's better done in person, I think, when we actually look at it and say, hey, if we really wanted to really get a good look at what we're talking about here, guys, how does that all work? Let me try to think here. The cosine of theta equals, as far as complementary angles are concerned, negative the cosine of pi minus theta. It gets a little messy. Is that true? Yeah, sure looks like it. So part of you thinking, is that even true? I mean, it looks like it is. The way they the way they have it written there. If you looked at the unit circle, if you had, you're talking about here, like a theta right here, that thing divided by r, that height right here, y, that y divided by r is the sine of theta. Here, that's also a height y. This is 180 minus theta, or pi minus theta. So that's certainly true. The cosine of theta is a positive number divided by a positive number. It's a positive answer. This is an exact same triangle, just flipped over here. Yeah, I know, but this is a negative direction. If this is x, that's negative x, and that's r. Negative x over r is the cosine of 180 minus theta. Negative x over r. If you multiply negative x over r by negative 1, you get x over r, which is this guy. Well, okay. I mean, if we're going to say that, we can say that. It's true. Now, you probably want to, okay, why? Why does he keep saying this? Well, hear what I said here. This doesn't tinker too much. This doesn't mess around too much. This is just the way it is. This is the same exact size as that, only the signs are opposite. If this guy's a positive difference, then this delta theta here is a negative difference, because negative times negative would get you the positive. If this is positive, Positive times negative will give you a negative answer. This is a negative distance. If this is a negative difference, this must have been a positive one because -1 times the positive would give you the negative. Same kind of argument here. Make a long story short, they're opposite signs of one another. Same magnitude, same delta theta. Delta theta prime and delta theta are the exact same size. Opposite in sign, however. They have the same magnitude, but they're opposite in sign. d theta prime and d theta are the exact same size, only opposite in sign. They have the same size, they have the same magnitude, but opposite signs associated with them. Same thing here. Same magnitude, but opposite signs associated with them. Okay. Okay, true. Fine. So what? Well, and then pi is the 180 that we're talking about, right? I just want to keep saying, switching between the pi and the 180. We can do that. We just know pi means 180. 180 degrees means pi radians. Okay. Yeah, okay, great. So what else can we say here? There's one other thing that's kind of coming to mind, that should be coming to mind. For some reason, I'm kind of missing it. It's a question of how you want to define a lot of stuff that you're doing, guys. That's for sure. Okay, let me just look really quickly. One other thing that really needed consideration. Yeah, what is it? What the heck does all this mean? It means exactly what I'm about to say. Sine of theta equals the sine of theta prime if theta plus theta prime add up to 180. I'm not going to go all the way around that unit triangle. I'm not going to go all the way around that unit circle with the triangles. I'm going to deal with 0 to 180. 0 to 180 degrees for our purposes. That's all that we need to deal with. If theta, if we're looking at this, if theta plus theta prime equals 180 degrees or equals pi, theta plus theta prime is 180 degrees or equals prime. And that also means that the cosine of theta equals -1 or the opposite of theta prime. If by definition we're working right here. Okay, I mean, you're going to have the feature of being able to take this back, of going backwards with the film, because I'm going to, obviously I can't, given the size, great blackboard here, guys, everything's working, the chalk is great, everything's great, but, given the size that I'm writing, even if I was writing much smaller, some of this stuff's going to have to go initially. So these two right here, given this circumstance of the reality, theta plus theta prime equals pi, theta plus theta prime equals pi radians, or theta plus theta prime equals 180 degrees, mean the same thing. These two realities are identical to this, because this is theta, and that right there is theta prime. This is theta, and right there, that's theta prime. This is theta, and right there is theta prime. Okay, I got it. Since I was using pi right here, well, so what? You already had the 180. It's true with the 180. Let me be consistent with the pi right there. They add up to 180 degrees, known as pi radians. Okay? All right. Long song and dance here. I guess we got to remember a bunch of things. We got to attack what ds is. Well, ds is going to have a definite answer vis-a-vis the way they traditionally determine the derivative of the function, of many functions, in fact, many trigonometric functions. They're typically, my suspicion is, I'd have to look at some old notes and some old books and stuff, some great books out there, but I think they're dealing with the acute angles to a large degree. They're dealing with angles that are within the triangle, at least when they're trying to give a gut explanation to what's going on. That's sort of their language. Whole bunch of ways to talk about it, guys. Whole bunch of ways to talk about it. Tell you what, I mean, unfortunately, I got to erase some of this stuff, but just remember it. Remember what I said here, it's going to come back. Let's talk about ds. Well, I'll tell you what, there's got to be a way to visualize some of this stuff, and it's stuff I've done in the past. Forgive me, you already saw this, but I'm trying to keep it within the context of a prior discussion. Everyone, right here. That's the ds right there. How good the chalk is going to show up if I keep doing this kind of stuff, but there you go. There's the ds. Yeah, we got to talk. Well, the way I'd done it last time was I said, can we somehow find s to be a function of theta, and then I can go ds d theta. Yeah, I think we do a lot. There is ds, and that's this length right here. Tell you what I'm going to do. What do you say, because the r changes, the small r changes, but the big R does not. Big R does not change. You understand the tangent of theta is opposite. I'm not getting the tangent of theta, but I just want to talk to you about it for a second. Everyone understands that the tangent of some theta here is the length of the opposite side divided by the length of the adjacent side. True. What if you reverse that and you took the length of the adjacent side and you divided by the length of the opposite side? That's the reciprocal of the tangent function. That's 1 over tan theta. That's not tan theta, that's 1 over tan theta. 1 over tan theta would be for this big angle right here, for the inside angle now, guys. The inside angle. And see where we can see this. This would be theta 2, theta 1. Okay, there's a lot here. There's theta 1. Here's theta 2 prime right here. And there is no, I mean, I don't think Houdini could get himself out of that one. But let's see here. This is theta 2 prime right here. All right, inside right here. And theta 2 is on the theta 2 is on the outside. Theta 2 prime is right here. All right. Why don't you get the tangent of theta 2 prime? Why don't you get the tangent of theta 2 prime is capital R divided by this big length from I don't, guys, if I write any more on this, we're not going to see anything, but this triangle right here, the relatively big one right here, the tangent, and this is theta 1 prime is on the outside. Theta 1 prime, theta 1's on the outside. Forgive me, I know this is not going to be too legible, guys, if at all. But here's theta 2 prime right here. The tangent of theta 2 prime is the opposite, capital R, divided by the adjacent, which is some length, we'll call it S2. S2. Sure, but I want to do something different. I want to go 1 over the tangent of theta. I want to go 1 over the tangent of theta. 1 over the tangent of theta. 1 over the tangent of theta 2 prime is the adjacent length divided by r. And if you multiply that by the adjacent length divided by capital R, and if you multiply by capital R, you actually get that length right there. See, I want to find out what ds is. And I guess the way to find what ds is, let me just say it's, to find what ds is, let me just find what delta s is. And delta s is going to be s sub 2, a long length, minus a short length. This guy, I mean, for our purposes, we're going to say that approximately, if things get small enough, ds equals delta s. Well, I'm going to say, why don't you find 1 over the tangent of theta. We already said tangent is opposite over adjacent. I don't want that though. I want adjacent over opposite, which is the reciprocal of the tan of theta. It's 1 over tan theta. 1 over tan theta is this divided by that. Times that will give you the length of this guy. And that's for theta 2. And that happened with theta 2 prime. And the other one, let's get a bigger angle. Because here's theta 2 prime, and it's not a real big angle. Not compared to this guy, theta 1 prime is bigger. Let's get the 1 over tangent of theta 1 prime times capital R, that'll give me that length. So I got the big length minus the small length, I'll get that length. One over tan theta 2 prime minus times capital R, and 1 over tan theta 1 prime times capital R will give me ds. Will give me delta s. Yeah, let's keep it in mind. We delivered this speech ad nauseum now, right? I mean, theta 2 prime is more compact, doesn't open as much as theta 1 prime does. This is a smaller angle than theta 1 prime. Yeah, this one doesn't open as much. Theta 2 prime may not open as much, but there's a bigger length associated with it than is associated with theta 1 prime. Theta 2 prime is a smaller angle than theta 1 prime. So let's see what we can say here, guys. Let me kind of rewrite this a little bit. So a little bit more room. Can write a bunch of ways, but I mean, the prime's the inside. True. Yeah, I got kind of an idea. Divide by delta theta prime. Divide by delta theta prime on each side. Fair enough? If you take it to the limit, I'd be really careful here. Extremely careful. Just because of the symbolism more than anything else. If you take the theta primes and bring them down here, take the theta 2 prime and bring it down this way, because that's really this. This is theta 2 prime minus theta 1 prime. This is, so theta 1 prime is bigger than theta 2 prime. Theta 1 prime is bigger than theta 2 prime. What does that mean? Well, they're both positive, and theta 1 prime is bigger than theta 2 prime. Theta 1 prime is bigger than theta 2 prime. That's going to be a negative answer on the bottom. It's going to be a negative answer on the bottom. What about here, though? Here, the inverse tangent of theta 2 prime is this length divided by that. That's a pretty big length. Compared, that's the, I hope I didn't say inverse tangent, I didn't want to say that. The 1 over tan theta evaluated at theta 2 prime, the 1 over, and we're using radians, and we're using the inside, we're using the insides, and we're using radians. The 1 over tan theta 2 prime is this long length divided by capital R. The 1 over tangent theta 1 prime is this short length divided by R. Whoa, this length is longer than that length. And this length is associated with theta 2 prime. And this small length, the long length is associated with theta 2 prime. It's associated with 1 over tan theta 2 prime. And this short length is associated with 1 over tan theta 1 prime. Big minus small is a positive answer. Positive answer here, negative answer there. Positive divided by negative is a negative answer. A positive difference divided by a negative difference is a negative answer. If you take theta 2 prime and have it approach theta 1 prime, this is always, always, always a positive answer, and this is always, always, always a negative answer. Positive divided by negative is a negative answer. You are finding the derivative of this. You're finding the derivative of this. In the limit, as delta theta prime goes to 0, this goes towards 0. ds d theta prime times R. Sure. If you multiply by d theta prime on each side, you're going to get ds. Yes, you're going to get ds if you're dealing with positive going to negative. Prime's going from a small value of pi over 2, 90 degrees, a value of pi over 2, and pi over 2, which is 90 degrees, and all the way as this works its way upward, theta goes towards 0 radians. Pi over 2 radians to 0 radians. So, pretty fascinating stuff. So you're getting this. Yeah, I guess if I take the differentials, work the game here, I should be able to get this. Should be able to get this. Yeah, it'd be nice to see what that is. I mean, at the end of the day, right? All right, guys, so this is kind of where it's working. I'm going to use the primes for now. I almost don't want to use the primes because I think what they're using, their idea of a theta is the theta inside of the right triangle. The theta inside of right triangles, the angle inside of right triangles, they call theta. I'm calling it theta prime. And I'm going to call the outside thetas. I'm going to call the stuff that's out. I'm going to call all the exterior angles. I'm going to call all the exterior angles thetas. All the interior angles in the right triangle, at least the ones that are associated with what we're doing here, the exterior angles I'm going to call theta. The interior angles that we're dealing with, I'm going to call theta prime. They're usually calling them just theta, and that's where they're getting that definition. So, but you got to make sure you're speaking the same language, guys. So you're looking at it like this. So what is this? What is this d tan theta prime over, the whole thing here? We do it. Right. So let's see what we can say here. I mean, we can employ some of this stuff. We can employ a lot of stuff, guys. Let's see what we can say here. If you're going to do it, let me use what's here. We got this. You guys got the feature that you can erase. Let's go with let's just go this d theta. Let's find out what it is. And again, we can always come back, or you can always come back a lot easier at this point while you're watching this, and I can watch it too. What's going on here? Well, we've done this before, guys, but we're just giving it a little different look. D 1 over tan theta prime. We're dealing with the interior angles just for the heck of it. I'm going to see how it works on the outside angles. The outside angles behave differently. How? Well, we just said the delta theta and the delta theta prime are equal magnitude, only opposite in signs. The d theta and the d theta prime are equal magnitude always, but always opposite in sign. But the differences are the same. This is kind of the strange thing. I mean, here on the outside, let's talk about the outside for a second. The theta 2 on the outside and the theta 1 on the outside. Theta 2 is bigger than theta 1. Yeah, and the 1 over tan of theta is bigger associated with the theta 2. 1 over tan theta 2 is bigger than 1 over tan theta 1. True. Whereas, yeah, it's absolutely true. But absolutely true. And you're saying, well, so what? You're not saying anything profound here. 1 over tan theta 2. 1 over tan theta 2 is a bigger, the reciprocal of the tan theta 2, the reciprocal of the tangent function. 1 over tan theta 2, right here, 1 over tan theta 2 is a bigger answer than 1 over, so 1 over tan theta 2 is a bigger answer, and these are all on the outside. 1 over tan theta 2 is bigger than 1 over tan theta 1. Yes. Yeah, similarly, 1 over tan 1 over tan theta 2 is bigger than 1 over tan theta 1. Similarly, 1 over tan theta 2 prime is bigger than 1 over tan theta 1 prime. True. Always. It's bigger than that. In fact, they're the same size. 1 over tan theta 2 prime equals 1 over tan theta 2. 1 over tan theta 1, prime. 1 over tan theta 2 prime equals 1 over tan theta 2. 1 over tan theta 2 prime equals 1 over tan theta 2. 1 over tan theta 1 prime equals 1 over tan theta 1. Yes. What does that mean? That means that the difference between this and this is identical to the difference between this and this. Same exact size, same exact magnitude, same exact sign as well. That doesn't vary. That's not an issue. Signs are okay. The difference is, with this one right here, this theta 2 prime, forgive me, right in here, yeah. This theta 2 prime is smaller. This theta 2 prime is smaller than this theta 1 prime. This theta 2 prime is smaller than this theta 1 prime, whereas this theta 2 is big. As much as this is big, that one's small. This one's big, that one's small. This one's big, that one's small. Yeah, not only that, this is bigger. I mean, so in other words, if this gets bigger, that's going to be smaller. The theta 2, theta 1 is positive. Equals a negative delta theta. This right here that's negative. Theta 2 prime minus theta 1 prime. Theta 2 prime minus theta 1 prime is negative. Right. Theta 2 minus theta 1 is positive. Is positive. How do they relate to each other? They're the exact same size, only opposite in sign, whereas the difference in the tans are always the exact same sign. What does that mean? If I do a d 1 over tan prime theta, if I do a d 1 over tan, can't even talk here. Hold on, let me try it one more time. If I do a d 1 over tan theta prime d theta prime, and I compare it with d of 1 over tan theta d theta, they are equal in magnitude always, but always opposite in sign. Unless you get a 0 in there somewhere. That's not what we're worried about. If indeed that's even possible. That's huge. These guys are always opposite each other, guys. They're the exact same size in terms of magnitude, but opposite in sign. This difference right here, you guys, the difference between these two, do a subtraction, and the difference between these two is identical. The tops are the same. So if you ever did, I don't, there's so much of this you don't want to erase just yet, but I mean, so remember that. So if you ever did, and I guess herein lies the whole situation. If you ever did d of 1 over tan theta prime d theta prime and compared it to 1 over tan theta d theta, they are equal in magnitude. They have the same absolute values. They're equal Except you got to multiply one of them by -1 for them really to be. They're equal magnitude. They're opposite in signs. This top differential doesn't change. According to what I defined to be theta and theta prime. Theta and theta prime. How I did all this game right here. Theta and theta prime. According to that, that's fine. It works. That's huge. That's huge. Sine theta is capital R over R. As we've already said, we've done this. We did some games here with this. Keep talking. We're eventually going to get back to some of this stuff. Wow. Yeah, okay. So all I got to do is find one, and I find the other one, how it works. This is where the signs were getting messed up. To make a long story short, that's where the signs were getting messed up. We knew that there was a way out. We had a gut feeling that was happening, but this is a more or less. I don't want to make it sound, I don't know how rigorous this is, but this is more or less a rigorous look as to why the signs are an issue sometimes, and you got to watch it. It's bigger than just blindly writing something down, which I'm guilty of doing as much as anyone else is guilty of doing. When you got it to here, that's huge, and that's where that all was coming from, guys. Now remember, usually this prime business, my gut is telling me that's where they're going. This theta prime that I introduced or that I'm talking about in the language that I'm choosing to talk, that theta prime is what they're usually working with as the theta. Whatever's interior to the right triangle, how those interior angles, not exterior angles, this is the exterior angles in our language, but usually they call the theta the interior angle. What I'm calling theta prime right now. Those interior angles, what is going on? Well, the interior angles are interesting. The interior angles are, you got a theta 1 prime, which is pretty big, and then you got a theta 2 prime up here. You're moving that way. You're moving upwards. How are you moving? Well, let me see how you're moving. You're moving from any number of ways that you want to move, I guess you could say. The derivative can be done any way you want, whatever direction you want. It's going to come out just fine. What are we talking about? Well, theta 1's a big number. Theta 1 prime is a big angle. Theta 2 prime is a smaller angle. I'll say big and small. Theta 1 prime is a big angle. Theta 2 prime is a small angle. Small minus big is going to be a negative answer. Negative answer, huh? Yeah. Small angle in the interior, theta 2 prime, minus big angle in the interior, theta 1 prime, theta 2 prime is a small angle. Theta 1 prime is a big angle. Small angle minus big angle is negative answer. Yeah, but associated with the small angle is a big 1 over tan theta prime function. It's a big 1 over theta. It's a big 1 over theta. It's a big 1 over tan theta prime value associated with that small angle. And here, there's a small 1 over theta prime answer associated with the small angle. Associated with the big angle is a small theta prime, associated with theta 1 prime, a big angle is a small value for 1 over tan theta prime. Associated with the big angle is just a small length right here divided by this for the 1 over tan theta prime. The 1 over tan theta prime associated with a big angle is a small value. 1 over tan theta prime is a small value when you're talking about theta 1 prime being big. When you're talking about theta 2 prime being small, you get a big 1 over theta, you get a big 1 over tan theta prime answer. So, for the small angle theta 2 prime, there is a big 1 over tan theta prime for an answer. And for the big theta 1 prime, there is a small 1 over theta. There's a small 1 over tan theta prime for an answer. What do you mean? Well, that means small with the tan theta 1 prime, big, small with the tan theta 1 prime, small with the tan theta 1 prime, and big. Small with the theta 1 prime, and big with the theta 2 prime. So you got the theta 2 prime, big answer for 1 over tan theta prime. And for the theta 2 prime, there is a big 1 over tan theta prime. For the theta 1 prime, there is a small 1 over tan theta prime. Big minus small is a positive answer, but this is small minus big on the bottom. Small minus big on the bottom is negative, and on top, big minus small is positive. It's going to be a negative answer. So the way they did it, sorry guys, this stuff is, like I said, it's got its own dynamic, I guess. Any way you want to do this now? I mean, so I want to say there's other things you can look at, guys. There really are, but that's neither here nor there. We're not going to worry about it too much. We're going to say 1 over tan theta prime d theta prime, and we're going to get. See what we're going to say here, guys. We're going to say, okay, these are all interior guys going on, right? Well, how does the derivative of the tan function go anyway, man, to be honest with you? We're not going to worry about the primes, guys. The primes are just angles that we're all used to using anyway. So this right here becomes d of 1 over sine theta prime. Well, wait, let me just write this better way, guys. Really? Yeah, you know it's true. Get the derivative with respect to this. You know, it's not really within the actual context. Everything is consistent with itself. So the derivative will be the same thing you're used to seeing, but then we're gonna play a game. You know, what do you call it? You could call this theta, and you call rather than theta prime, call it theta. Rather than theta prime, call it theta. Call it theta. Call it theta. Call it theta. No big deal. As long as it's consistent within itself, you're still going to get the right derivative. You're going to see what happens. You know, there's a lot to say here. There's a lot to say. But, you know, we'll see what we need to say, I guess. This is the derivative of f over g, of f of theta over g of theta. What is that? That's g f prime, which is minus f g prime minus f g prime over negative 1 sine squared theta prime plus negative 1 times cosine squared theta prime true. This very well-known identity, sine squared of some, call it phi if you want, phi, doesn't matter. Sine squared theta prime plus sine squared theta prime plus cosine squared theta prime is 1. 1 times negative 1 is negative 1. It's negative 1 over sine squared theta prime. True. That's equal to this. Absolutely true. If it's on the inside like that. Yeah, it's the thing we're used to seeing. 1 over sine squared theta for the derivative of the cotangent. Correct. Yeah, true. That's what that equals. What does that equal then? What does this equal? Well, wait a minute. If you're going to get a negative here for an answer, it's got to be a positive. That was kind of the thing. That was kind of the thing. Look right there. Look carefully right here, guys. If they're different like this, if I multiply both sides by negative 1, d 1 over tan theta d theta, multiply by negative 1 on each side. Negative 1 times negative 1 is 1. Negative 1 times this, you end up getting, basically you already said they were opposites of one another, guys. You don't need me to write that again. I mean, but I can just, d 1 over tan theta as I had it described. These are the outside guys. Usually they put the theta, their definition is there on the inside. That's usually the way, I'm convinced that's the language they got to be using to get that. This guy's equal to the opposite of what I just drew is a conclusion. Prime. Equals negative 1 times negative 1 over sine squared what is that? Negative 1 times negative 1 is 1 over sine squared theta prime. Let's talk about it. Negative 1 times negative 1, negative 1 times negative 1, yeah. When two things are supplementary, their signs are always equal, at least in the realm from 0 to 180 degrees. We can look at some other stuff too. I mean, there's probably stuff we can do. But for our purposes, from 0 to 180 degrees inclusive, and that's a lot of what we're dealing with right here. That's all we need right here. So we don't want to get too adventurous about this. This is sine theta. This is sine theta prime. I mean, this is pretty important. I mean, what I have written up here, I mean, there's another way to speak the language. Well, actually, there's not only another way to speak the language. We already spoke that language. It's right here. What am I worried about? Sine theta equals sine theta prime for 0 to 180 degrees. From 0 to pi radians, or from, said another way, from 0 to 180 degrees, sine theta equals sine theta prime. Sine theta equals sine theta prime. It's pretty crazy. Sine theta equals sine theta prime. Indeed, sine theta equals sine theta prime is this. And that might have been what was getting us in trouble. The other one, this is very important, and this is another thing to think about. Depending on the angles under consideration, guys. The difference in the angles, as long as you're associated in the right place with the angles, you got this as an angle. What's going on here? This is pretty crazy. The other one had this. Really? Yeah, well, if that's the case, it's the same as that. And that'd be this, and that came from this. If it came from that. So wait a minute, what's going on here? I mean, in all this mess, there's got to be a conclusion. We got to be speaking the same language. It means that d 1 over tan theta prime d theta prime was equal to negative 1 over sine squared theta prime. That's the same, with caution, with great caution, that's the same as this. If you use theta or theta prime, the complements don't change what the derivative is. Obviously, there are different angle measurements. If theta prime happens to be, I don't know, it's probably easier if we use degrees here. If theta prime happens to be 60 degrees, theta is 180 degrees. So you want to kind of stay with the angle you're dealing with. If this is 60 degrees, which is pi over 3 radians, if this is pi over 3 radians, this is 2/3 pi radian. This is 2/3 pi radians if this is 1/3 pi radians. It still works. Absolutely. So you can deal with the prime. Leave it with the prime. Notice the d theta prime, the d theta prime and the d theta are always equal magnitude. They're just opposite in sign. And that came out to, as we said, it was going to be something different. They're not the same. Even if you put the prime in here, they're not the same. It's 1 over sine theta prime squared, not negative 1 over sine. This is negative 1 sine theta prime squared. This is negative 1 the sine of theta prime squared, and this is positive 1 the sine of theta prime squared. You can put a theta prime here, or you can leave it as a theta. They are different. if you're dealing with but they're the same size. They're the same size as it goes on. That's the big thing. There is a difference. You know, you could put a prime right here and leave the prime there, and they differ by a factor of -1. They are opposite in sign, equal in magnitude. Put a theta prime here, you can put a theta prime there. One's 1 over sine theta prime squared, 1 over sine theta prime squared, and this is -1 sine theta prime squared. This is -1 over sine theta prime squared, and this is +1 over sine theta prime squared, or this is -1 over sine theta squared. Yeah, sine theta is the exact same answer. Different theta, but they're complementary. The differences are equal. Perfect example. The difference between 80 degrees and 60 degrees, 80 degrees minus 60 degrees is 20 degrees. The supplement of 80 degrees is 100 degrees. The supplement of 60 degrees is 120 degrees. 100 degrees minus 120 degrees is -20 degrees. There's still 20. 80 minus 60, 80 minus 60 was +20. The supplement of 80, 100, 80 minus 60 is 20. The supplement of 80, which is 100, minus the supplement of 60, which is 120, 100 minus 120 is -20. 20 and -20, yeah, that's just a -1. If I want to find the sine of 100 degrees, it's the same as the sine of 80 degrees. If I want to find the sine of 120 degrees, it's the same as the sine of 60 degrees. That's kind of the argument all the way. But there is a negative here and there's a positive there. And that was really what was going on there, guys. That was the one thing that was a little, there's more to it than just blindly writing down the answers. No matter how you're going to do this thing. But one's, depending where you want to go. Let me leave it in this language. One's negative. The inside guy is a -1 over sine squared theta prime. The outside guy is a positive. Why is the outside guy a positive? The outside guy's a positive because this guy on the outside, the theta 1 right here, is a pretty big angle. Yeah, theta 2 is even bigger. So as you move upward, theta 2, as you move upward, the angles get bigger than the prior angles. Theta 2 is bigger than theta 1. Theta 2 minus theta 1 is a positive answer. And 1 over the tangent of theta 2 is this big long length divided by this constant length. That's 1 over the tangent. 1 over the tangent of theta 2 is this long length divided by this constant length. And that's associated, so associated with the big outside angle, this long length divided by this constant length is a big answer. Associated with this small outside angle, this small length right here divided by this constant angle is a small answer. So as thetas get bigger on the outside, the difference between 1 over tan theta, the difference between 1 over tan theta, the 1 over tan thetas get bigger as the thetas get bigger if you're talking about outside angles. But when you're talking about the inside angles, as the inside angles get bigger, as the inside angles get smaller rather, the tangents get smaller. So say that one more time, it's important. As the exterior angles get bigger, the 1 over tan theta, as the exterior angles, theta sub 2 opens pretty big. So does theta sub 1, but it just doesn't open as much as theta sub 2 does. The more up you go, as you're moving upward, the thetas get bigger. Theta sub 2 is bigger than theta sub 1. And the 1 over tan theta of theta sub 2 is this long side divided by this constant. And so the big angle is associated with a big 1 over tan theta. And the small angle is this small side divided by this constant length side. The small angle has a small 1 over tan theta. The small angle on the outside has a small 1 over tan theta, and the big angle on the outside has a big 1 over tan theta. Wow! As the thetas get bigger, the 1 over tan theta gets bigger. That's hardly going to be a derivative that's negative. If the top is a positive, if the top gets bigger, if the 1 over tan thetas get bigger as the exterior angles get bigger, the difference between 1 over tan thetas is positive. The difference between thetas on the bottom is positive. So on top, the 1 over tan thetas keep getting bigger, so the difference between the 1 over tan thetas are positive answers. And on the bottom, as you proceed upward, thetas get bigger, so the difference between the thetas also get bigger. As we're looking at what I just said, the 1 over tan thetas, keep getting bigger. What does that mean? Well, the delta 1 over tan theta is going to be a positive answer. And on the bottom of the fraction of the ratio, the thetas keep getting bigger, so the delta thetas are positive. Delta 1 over tan theta is always going to be positive, and delta theta is always going to be positive. So delta of 1 over tan theta divided by delta theta is always positive. So if you're going this way, you're always going to be getting a positive answer. If you're this is for the exterior angles. For the exterior angles under consideration. Forgive me from writing it right in the equation, guys, but there it is. Yeah, for the exterior angles. For the interior angles, the same exact thing's happening. As you go up, the long minus the short is a positive answer, yes, but the interior angles don't get bigger like the exterior angles get bigger. The exterior angles get bigger, but the interior angles get smaller. So it's going to be small minus big is a negative number on the bottom. Positive divided by negative is a negative answer. And that's where it came from. And that's where and this really is the way, I'm not trying to invent new math here, guys. This really is the answer, because I'm sure their criteria is look into the interior of right triangles, not the exterior. We're going to look at the exterior and the interior, and we're going to get the same answer each time. Got to remember who's who, though. That's the only thing. Well, we just did it. So let's stay with, hey man, there's a whole bunch of ways we could look, isn't there? We could use theta as the exterior angles or interior. Let's use the exterior. Let's play the game there, and then you can go interior if you want as well. These are interior. Exterior, watch your step, because you usually don't see it like that. It's 1 over sine squared theta. Okay. And that's the exterior. Well, yeah, don't want to be using different colors here, guys. That's interior. That's interior. And that also is interior, right here. All right, it's thoroughly a mess at this point, guys, I know. All right. Okay, what the heck? You know, what did we say? Well, we did this dance quite a bit. We said ds d theta was equal to r d r d and I'm going to stick with the I'm going with the outside right now. I'm just going to stay with the outside. It was that, right? We did this. If you do d theta, of d 1 over tan theta d theta, you get the d of 1 over tan theta times r, you'll get the ds. The delta theta will cancel for our purposes, and we got ds. Right? Absolutely right. Now we said these are the exterior guys. If these are the exterior guys, this right here is 1 over sine squared theta. Yeah, true. Yeah, according to what we're doing right here. Yeah, according to the way we're playing the game. These are the exterior guys now, right? Let's put in place of ds this. R times 1 over sine squared theta d theta. Yeah, okay. That was the ds. Remember, there was a ds here, guys. You have it on the film. It was there. I did this. Okay. dB equals, have that r and r squared cancel. Have the I right here. This is sine squared theta on the bottom. This is on top. This is I sine cubed theta over 1. You know what I mean? And this is 1 over that. So these cancel. You know where I'm going. Sine squared theta into sine cubed theta is sine theta. The big R and the big R squared canceled. The I you bring over here. You've got this. You'll get the magnitude of B magnitude of B. Yeah, now we got to be careful. Man, we really did the song and dance here, guys, didn't we? Yeah, tempted to put a negative right here. We didn't. I mean, you know that. We delivered a whole speech on why you don't do that here if you're going to start down here. And you're getting half. And when I get the entire, not half, when I get this semi-infinite, when I integrate over this semi-infinite length wire, when I get an answer, I'll double it and I'll know the whole wire. Okay. If this R comes down here, what is the outside angle out here? Bring this R all the way down here and make it perpendicular on both sides. It's a 90-degree angle. If you go this way, it goes to 0. So, forgive me. No, I'm wrong. No, what am I talking about? Forgive me. You bring this thing all the way down to here, it's perpendicular to here. You bring this thing all the way down to here and it's perpendicular to the wire. Bring this all the way down to here and it's perpendicular to the wire. That's a 90-degree angle. On the outside, it's a 90-degree. On the outside, it's a 90-degree angle. Open this thing all the way up and go toward infinity. The outside is 180 degrees. It's 90 degrees. This is not a final answer. This is 90 degrees to 180 degrees. True. That's pi over 2 to pi. Here goes. The integral of the sine function. Okay, guys, hold on just 1 second. I got to take one break here. Okay, guys, welcome back. Let's just finish this thing out. What do you got? On the top part of this, we've got, is negative cosine, we said negative cosine theta. Negative cosine theta. Cosine theta is negative cosine theta, so we'll get the negative in a second. Negative cosine theta. Cosine theta, let's go up here. Cosine of pi is negative 1. The opposite of negative 1 is 1. Pi over 2. Cosine of pi over 2 is 0. 1 minus 0 is 1. For the semi-infinite, semi-infinite. Double that, and this is consistent with Ampere's law. Look at that. Fully consistent with it. Semi-infinite. And infinite. Look at that, Ampere's law. Proven. Could you, that's it. That's why it works, you guys. That's why it works. That's why it works. Would we have gotten the same answer with the negative right there? You know, the negative as it's getting. Yeah, you'd go pi over, here you'd start on the inside. It'd be pi over 2 going to 0. The integral for the inside, if it would have been, now, that's that. Now, what if for the other one? You know, negative theta prime, d theta prime, all that business. That comes out what's that? Well, okay, I said negative this time. Yeah, because we're dealing with the other one. We're dealing with this thing getting smaller as we go up. Well, it gets smaller as the angles get smaller. As the angles get smaller, it still gets bigger. Why don't you go from the inside being pi over 2? Earlier we started with the outside being pi over 2 and then worked up to an outside being equal to pi. We went from pi over 2 to pi. Here we're going to start with the inside being pi over 2 and then the inside going to 0. Yeah, that'll work. Well, I shouldn't speak too quick. I mean, hopefully it works, right? We'll see it. So when you actually do this, you do this, but there's a negative right here. There's a negative right there. There's a negative right there. There's a negative right there. Put the negative right there and go from 0, go from pi over 2 to 0. There it is. Watch. Put a 0 in here for theta prime. At this point, it'd be theta prime. Because we're using theta primes. It's a different label, the same argument though. Theta prime. Put a 0 in for theta prime. For the top. Remember now, you take this thing on the inside and you go that way, the inside's going to be 0 and the outside's going to be pi. The outside's pi when I was dealing with the thetas, and the outside was pi over 2 all the way to pi. Pi over 2 all the way to pi. With the inside is also pi, because they add up to 180, pi over 2 and pi over 2 is pi. But then on the inside, it goes from pi over 2 to 0. What is the cosine? Put a 0 right here. Put a 0 right here. Cosine of 0 is 1. The opposite of 1 is negative 1. The opposite of negative 1 is 1 again. Pi over 2 in here, cosine of pi over 2 is 0. 1 minus 0 is 1. Do it again. Here's 0. Here's a 0. Here's a 0. So, here's a 0. Put a 0 right here. Cosine, put a 0 right here. Cosine of 0 is 1. The opposite of 1 is negative 1. The opposite of negative 1 is positive 1. That's positive 1. Put pi over 2 right here. That's 0. 1 minus 0 is 1. Same answer. You just have to have the limits of integration right to do this. All right, forgive the break. I had there's something I had to attend to really quickly, but there it is. So we put it together. These last two films have just been put together for you like this, and this should be straight. Fascinating stuff. It's not just about what we know about the mathematics. Are we flexible enough to use the mathematics in a way? Are we flexible enough to use the mathematics in a way that maybe we didn't think of using it in that way? We just don't fire off equations and identities without looking at their significance. And is there another way to look at what's happening? If there's another way to look at what's happening that's consistent, that's mathematically consistent with everything that's going on, it's mathematically consistent with everything that's going on, but you got to be careful what the mathematical quantities are. Frequently, the magnitude of the mathematical quantities won't change, but the signs can change. And that happened here, and if we were careful with how we were evaluating everything, we got the exact same answer no matter how we did it. With exterior angles, doing the integration with exterior angles, the thetas, or doing integrations with interior angles, angles that are interior to the triangles that we're building, and we still got the exact same answers. That's something I just wanted to come back and talk about with you. Thank you very much for your time. Take care.